Okay, in this video, we're going to do the first part of the calculations for the solubility product experiment. So this is the solubility product of slightly soluble metal hydroxides. So we're going to use magnesium hydroxide as an example. I'm going to just make up some data to use to show you how to do the calculations. Of course, you will use your data from the experiment in your calculations. So we'll begin by talking about the solubility product. Magnesium hydroxide is sparingly soluble in water. It's not real soluble. It's a solid. When it does dissolve, it forms a small amount of magnesium 2 ions and then twice as many hydroxide ions. It's a 2-to-1 ratio. The KSP, the equilibrium constant, is the concentration of the metal ions, so that'd be magnesium, Mg plus 2. So the charge would be 2 plus, and the metal is Mg, times the concentration of hydroxide. But because there's a 2 as a coefficient here, it would be hydroxide squared. So it depends on the magnesium concentration, but it also depends on the hydroxide concentration squared. Multiplied together, you have your KSP. Okay. So let's scroll down to our data. So here's some data. Suppose that we measured the pH 3 times and we got 9.47, 9.52, and 9.57. Well, you add those three together and divide by 3, you would get the simple average, which would be 9.52. It's slightly basic, right? So that's the pH we're going to use in our calculations. The average pH is 9.52. So we're going to come down here and let's do this calculation. I already have the number there, but let's do the calculation itself. So the pH plus the pOH is equal to 14. So if we know the pH, we can find the pOH from this formula here. The pH, sorry, would be 14 minus the pOH. So pH equals 14 minus the pOH. Okay, sorry, we're trying to find pOH. My apologies. Put that back there. pOH would be 14 minus pH. And so that would be 14.00 minus 9.52, which equals 4.48. Okay, that's the number that was there originally. Now we can see where it comes from. Okay, so the pOH is a measure of the hydroxide concentration. It's a logarithmic measure, 4.48. Now we come to the next one, and we want to convert that to the hydroxide concentration. So to find hydroxide, you take 10 to the negative pOH. Okay, so for this particular example, the hydroxide concentration, let me get the correct symbol there, would be 10 raised to the negative 4.48. Now let me see if I can highlight this in Microsoft Word and put that up as a exponent. There we go, superscript it. Okay, so then when you do that calculation, you put it in your calculator, you get approximately 3.31 times 10 to the minus 4. And that would be molar, right? It's the concentration of hydroxide. So again, let's put that up as a subscript. There we go. And now we've got our hydroxide concentration. Of course, this would be a superscript as well. So 3.31 times 10 to the minus 4. I guess I can just copy and paste that in here. Okay, so that's the hydroxide concentration. That's table 2. Now we come to table 3, and what we're going to do is we're going to use that concentration of hydroxide to figure out the magnesium concentration. We didn't measure that directly. We didn't have a magnesium sensor in the water. We had a pH probe. So the pH probe can give us the hydroxide, but it can't give us the magnesium. But we can use simple stoichiometry. Essentially, if you want to look at it this way, every time one magnesium hydroxide dissolves, it forms one magnesium and 2 hydroxides. So that means you get twice as many hydroxides as you get magnesiums. So it's a 2-to-1 ratio. So if you know that the hydroxide concentration is 3.31 times 10 to the minus 4 molar, then all you got to do is divide that by 2 to get the magnesium, because magnesium is 1/2 of the hydroxide. Okay. Now, from a reaction table, essentially what you do is you say before you dissolve any of it, they're both 0. Then they dissolve because Q is less than K. You get plus X here and plus 2X there. So at equilibrium, this is X and this is 2X. So in other words, magnesium is 1/2 of hydroxide because hydroxide is 2X and magnesium is X. X is 1/2 of 2X. So all you got to do is divide the hydroxide concentration by 2 or multiply by 1/2, and that will give you the magnesium. Okay, so we'll put that, oops, so we'll put that over here. Okay, so the concentration of magnesium is equal to 1/2 times the concentration of hydroxide, which is equal to 1/2 times 3.31 times 10 to the minus 4 molar. Okay, so let's put all these up in superscript just so we have them that way. Looks a little bit cleaner. Okay, so 1/2 times that. And so that comes out to approximately 1.66 times 10 to the minus 4 molar. Okay, so superscript that. And now we've got our magnesium concentration. So there we go. There's our two concentrations. Let me just put this right back over here. Page break. There we go. Okay, so now we're ready. We've got those two numbers there. We're ready for the next one. So the next one is to find the KSP. So remember, the KSP is pretty simple. It's just the magnesium concentration times the hydroxide concentration squared, or X from the previous table for magnesium, and 2X squared for the hydroxide concentration from the previous table. So it says in this one, just copy the values, copy from table 3, right? So we just come back over here. Here's our hydroxide concentration, 3.31. Okay, so that's right here. And here's our magnesium concentration. That's right here. It goes right there. And now we're going to calculate the KSP. We'll do that over here. Okay. So KSP equals concentration of hydroxide. Well, let's put the magnesium first. So magnesium concentration is right here. And then we're going to multiply that by the hydroxide concentration. Okay. And again, SP is subscript. There we go. And so what we end up with, I get about 1.82. 1.82 times 10 to the minus 11. And that's unitless because it's an equilibrium constant. And there we go. So now we've got that value right there. There's your KSP. Okay. Again, I just made these numbers up. I mean, I made the pH values up, but I think it's probably not going to be too far off from that. So there's our value. So now we're going to move over to the percent error. This is your fit table. Again, let me put this on the next page. Actually, you know what? I'll leave this up here. That way we can see the number previously. Okay. All right. So now we're just going to do a percent error, experimental value and then percent error. You may or may not remember how to do percent error. In general, percent error is the difference between the literature value, or sometimes it's referred to as the true value, the accepted value, the one that we believe is correct or accurate, minus your experimental value. And then you divide that by, again, the literature value. And then to convert it to a percentage, you take the whole thing and you multiply it by 100%. Okay? So literature value minus experimental. Now, sometimes you get negative values. So one way around that is to do what's called the absolute value. So I'm going to see if I can find the symbol in here for the absolute value. Actually, I don't see it anywhere over here. It's a straight line. There we go. Let's see, maybe we can do it this way. More symbols. It's just a straight line. So if you can find a straight line somewhere in the, there's quite a few symbols here, but I don't see any straight lines. So that's okay. Nothing there. Okay. Well, you know what I'll do? This is not exactly straight. It's slanted. It's a slash, but hopefully it gets the point across, right? So I'm going to take that little slash. It's not vertical like it should be, but we don't want to spend all day looking for this. Okay, so it's the absolute value. So remember what the absolute value function does. The absolute value of a positive number is just that positive value. The absolute value of the negative number is the positive of that value. So the absolute value of -6 would be just 6. Absolute value plus 6 would just be 6. Okay. So if you go and put your numbers in here, what you get is the literature value. I put them up here. 1.2 times 10 to the minus 11 minus 1.8 times 10 to the minus 11. And then that's going to be divided by the literature value, 1.2 times 10 to the minus 11. And then the whole thing times 100%. Okay, so it's not 1%, but 100%, sorry. There we go. And so what happens is, I realize these should be superscript 2, is that you actually get a negative difference. So if you take the absolute value, you get a positive difference. Okay. So it looks like I forgot to put the little parentheses here, right? So let's put the parentheses here. So let's do the slash to indicate we're doing the absolute value there. Okay, so absolute value of the whole thing. So what happens is if you didn't do the absolute value, you get a negative value, but that's okay. We get 50%. That's what it comes out to. Okay, so experimental value was this one right here. And actually it's 1.82, so we could put that 2 in there. And that's going to change it. It's going to make it a little bit less than 50, but if you round it to 2 sig figs, you get 50% error. And if you look at that number, it's pretty large, right? Normally, when we do experiments, we would hope to get a percentage error less than 50. But in general, KSP values lend themselves to pretty high percent error values. And so don't be surprised if you get a pretty high percentage, particularly for the copper 2 hydroxide. That one's most likely to be really high. But what we'll do in the calculations later on is we'll find there's a way to make these percentage errors a little smaller. And so we'll go through and do that one as well. Okay. So hopefully that helps you out.